but we will cover the basics here. So you should be good for the most part here. And then the main focus of the presentation, looks like I skipped over the agenda. The main focus of the presentation will be the bottom 4 items. I'll be focusing on a draft that has been the work has been going on that draft for the past couple of years. It's still evolving, but essentially it has been accepted as the guts of what EVPN multicast optimizations will build on. So I'll provide an introduction to what that draft, the new route types that the draft defines and what other processes, et cetera, are coming forth in that draft. So let's get started with some of the basics. Bump traffic. For those of you who are familiar with the multicast, the L2 multicast world, BUM stands for broadcast, unknown unicast, and multicast. By definition, this is multi-destination traffic. And whenever you have multi-destination traffic, concerns about throughput and latency, performance, convergence, all those things come into play. Bump traffic, if you have to think about it in a very basic way, think about an L2 domain, and a bump packet, which is a broadcast, unknown unicast, or multicast, it's just going to go everywhere in your L2 domain, okay? It's going to be flooded, right? So that's why I said whenever there's flooding, whenever a bump packet is in question, we have concerns about throughput, et cetera, right? Now, EVPN works the same as any other L2 protocol, so it does involve flooding of bump packets. What we want to talk about is how EVPN optimizes this over and above the traditional L2 protocols. I'm sure you guys are familiar with the IGMP snooping, IGMP proxy, all those knobs and handles that are available in the traditional L2 protocol, say like VPLS. EVPN integrates very well with all of them. And what we'll talk about today is how EVPN optimizes further. All those existing mechanisms with L2, EVPN optimizes even further. So bump traffic flooded everywhere in a L2 VPN domain. The 4 PEs, the 4 devices that you see on the screen, they are part of the L2 domain. So when a bump packet, which is sent by the CE, hits PE1, it is PE1's responsibility to propagate it or flood it everywhere. So that's your bump traffic. This is defined in the EVPN base RFC. If you are interested in receiving bump traffic, you have to send out an EVPN route. It's route type 3. It's also called IMET, or the inclusive multicast route. It's equivalent to your PIM star G. You want bump traffic, you want multicast traffic, you send a star G, you start receiving it, right? Same thing with EVPN. However, in EVPN, you accomplish it with the use of the IMET route, or the route type 3. So all these 4 guys on the screen, they'll send IMET routes to each other, which indicates, hey, I need bump traffic for this particular L2 domain. You have a chance to optimize further receiving bump traffic for an L2 domain. Now, it's the same 4 PEs. It's the same L2 VPN domain. But inside that domain, you'll see those red and green ovals. Those are bridge domains. Now, what is a bridge domain? Crudely, you can think of a bridge domain as a VLAN. Okay, so you have an L2 domain, and inside that L2 domain, you can have multiple VLANs. Now, if a service or a VLAN is not configured on a particular PE, so for example, here, the red VLAN or the red bridge domain is just configured on the top PEs, it's not configured on the bottom 2 PEs. So theoretically, any traffic that hits the red bridge domain that belongs to the red bridge domain need not be flooded to the bottom 2 PEs, right? This is an optimization compared to the previous slide where there were, the 4 PEs and it was a large L2 domain and everybody was getting every bump packet. In this case, we are able to abstract or go deeper one level to the bridge domain level and control bump traffic within that L2 domain, but now we are at a bridge domain level, the red and the green. how we communicate between bridge domains or how we communicate between the larger EVPN PEs is controlled by the use of the IMET route. One of the ways to do this, to accomplish this optimization of communication between the bridge domains or between the L2 VPN domains is P2MP replication. So what you're seeing on this slide on the top is the most basic way to replicate bump traffic. It's called ingress replication. The onus is on the ingress PE, which is shown on your left. The ingress PE, let's say, has to send packets to 3 receivers, as shown here. The ingress PE will replicate the same packet 3 times and send it out. So now you have tripled the amount of traffic inside your core by performing ingress replication. If you want to do better, you focus on the picture on the bottom, that is using P2MP LSPs. In this case, the ingress PE does not have to do that much of a heavy lifting. It is more optimized. It's not going to send out 3 copies of the same packet. It's going to send out 1 packet. And the 3 PEs inside that gray cloud, these are called bud nodes. So what essentially the function of these PEs is that as the packet comes in, they decide how many times they want to replicate it. So you have pushed the replication closer to the receiver and hence optimized it. So the difference between the top and the bottom picture is that the top is ingress replicated and the bottom is using P2MP LSPs. This process, these procedures are also defined in the base EVPN RFC today. What we'll be talking about, the focus for this presentation, is how to optimize this even further. If I don't have receivers behind any of these 3 PEs, I don't want the traffic to be flooded to them. And that's what the new route types that we're going to be talking about, that's what we'll be discussing. Now, this slide is not really a multicast optimization, but I wanted to talk about this since there's always some sort of a confusion around this. This is really a necessity to avoid loops in your access segment if you are using EVPN. I also want to use this slide to introduce the concept of an Ethernet segment. That is a very basic building block of EVPN. The blue oval that you see over there that spans the interfaces between the CE and the PE, that is an Ethernet segment. In this case, since the CE is multi-homed to 2 PEs, PE1 and PE2, it is obviously a multi-access segment. Now, if CE1 sends traffic to P1 and P1 sends it to P2 and P2 sends it back to CE1, it is very easy to form a loop in such a case. Traditional L2 protocols, they avoid this kind of a loop by the use of STP or shutting down some ports, that kind of thing. In case of EVPN, since we do have support for multi-access segments, we have the concept of a DF, right? You have a multi-access segment, you have a designated forwarder, and that guy does all the right things to make sure that loops are avoided. Now, we'll just go into a little bit of detail as to how this is done in EVPN. P1 and P2, they exchange EVPN routes, auto-discovery routes, Ethernet segment route. I'm not going to go into the details, but they're able to talk to each other, and they decide that they are part of the same multi-access segment. So when they send bump packets to each other, they will be adding an additional label, which is called the ESI label. This label helps to identify the Ethernet segment that the bump packet originated on. So for example, in this picture, CE1 or CE device sends the packet to PE1. Now, if CE1 had decided to send it to PE2, we would have less trouble because PE2 is actually the designated forwarder, right? So the designated forwarder always knows what to do the right thing in terms of loop avoidance and forwarding. But we cannot impose a restriction on the CE that the CE will always only send packets to the designated forwarder. In fact, this is against the spirit of EVPN, where we want to be able to utilize all the links between the CE and the PE. So really, we shouldn't have to impose a restriction on the CE that, hey, you are only supposed to send to the DF. So in our case, the CE decides that it's going to send to PE1. PE1 has prior exchanged the ESI label with PE2. That's why when PE1 sends this bum packet to PE2, it's going to slap the ESI label on the packet. When this packet reaches PE2, the DF, it is the responsibility of the DF to flood it. But when the DF looks at the ESI label and recognizes that this was the label that was assigned to the bum traffic originating on this ESI, it recognizes that it's the same, and that's why it should not forward it back to that multi-access segment. So it's the ESI label that kind of breaks the loop here, right? So this is again all part of the base RFC, the EVPN RFC. This was the first part of the presentation. These were the basics. Now we'll jump into the new stuff. This is currently, like I said, it's work in progress. It's being defined. It's being supported by multiple vendors, and I expect work will go on for the foreseeable future to further optimize what we have started. So for the rest of the presentation, we'll divide it into two parts. The big green oval on top is the core domain. We will discuss EVPN optimizations in the core domain. The little green oval at the bottom, again, that is the multi-access segment. Then we will discuss how EVPN is going to optimize the multi-access segment. So it's two parts. There's 3 new route types defined. For the core, or for the oval on the top, we are going to be discussing route type 6. That is the selective multicast route. We talked about the IMET route, or the inclusive multicast route earlier. We said that's defined in the base EVPN RFC. It's like a star G join. Now we will talk about the SMET route, or the selective route, which is like an SG join, if you want to draw a parallel to the PIM world. And that helps optimize EVPN traffic in the core. If you focus on the bottom oval, we will be talking about route type 7 and route type 8. These are mappings of the IGMP join and the IGMP leave, respectively. So for route type 6, the agenda for route type 6 is that it should be able to pull traffic from the core and only send it to those PEs that have a receiver sitting behind. If a PE does not have a receiver sitting behind it, we don't want to pull traffic down to that PE. Route type 6 is what helps us accomplish that, helps us accomplish optimization in the core. Route types 7 and 8, for those of you who are familiar with MVPN, it's exactly the same thing. In MVPN, we map, we convert PIM state to BGP state, right? Same thing that's happening here. We are converting an IGMP join to a BGP message or a EVPN message. So a route type 7 is a IGMP join sync route in EVPN. And all it is a mapping of a IGMP join, a real IGMP join that I have received on my L2 segment. Route type 8 is the corresponding leave message. So I'm not going to go into the details of how, and this is pretty standard stuff that works in the L2 domain with the traditional L2 protocols as well. The PE, the designated forwarder, has to perform the functions of IGMP snooping and IGMP proxy. So all those things are still in play. The DF acts as an IGMP querier in that access segment to keep the IGMP machinery flowing, and receivers sending queries, converting BGP messages to IGMP joins, that kind of thing. So all those things are happening. We'll focus on the EVPN portion of things. So to get all this started, one has to advertise this multicast flags extended community as part of your IMET route. So this is again defined in the base RFC. When you advertise this community, you essentially advertise, hey, I'm going to participate in IGMP proxy optimizations, or I'm going to be advertising the SMET route, the 3 new route types that we're talking about. This is what you need to advertise to get that mechanism going. So let's talk about the join sync route, which is the route type 7. If you look at the fields that are in the packet on the left side of the screen, it's pretty standard. You have the source, you have the group. You could do IGMP v1, v2, v3. The flags help you specify that. If you look at the top 3 rows over there, the first row is the route distinguisher. That's actually part of every EVPN route. The next field is the Ethernet segment identifier. This is the field that helps you identify the multi-access segment which we are trying to optimize, okay? The third row is the Ethernet tag ID. This identifies the bridge domain that we discussed earlier in the presentation. So you have to identify your larger L2 domain, then you identify the bridge domain, the sub L2 domain that we are trying to optimize, and then obviously the Ethernet segment identifier. So this is a direct mapping of the IGMP join into the BGP world. Now what exactly is going on here? You have a couple of receivers, the red and the green. Like I mentioned before, there should be no restriction on where the joins go. This is a multi-access segment. We should have the opportunity to equally utilize all the links. So receiver 1 decides to send a join to PE1. Receiver 2 decides to send a join to PE4. Now, what we need to do is reconcile these joins and propagate them to the DF. And we do this propagation using route type 7. So now the DF is your single point of representation for your multi-access segment and has all the information about all the sender, about all the receiver state across that multi-access segment. Once the DF has that state, it is then able to generate a route type 6 and send it up to the core to pull the appropriate traffic down. Route type 8, exactly similar to route type 7 that we just discussed, except that it's communicating leave state, right? We talked about the join, now we're talking about the leave. And just like the IGMP leave, this route becomes important in time-sensitive or time-critical applications. If your application is not time critical, theoretically, you don't need this route. Your IGMP state will just time out, as it does with regular IGMP. The leave times out. The same thing will happen here. In fact, this route was added later on in the draft. Originally, when it started, it was just the route type 6 and 7. And then for financial applications where the leave is also critical, this route was then added. So this is your route type 8, or the IGMP leave sync route. So what's happening here is you have your receiver 1. It sent a IGMP join to PE1. And PE1 said, OK, I have to propagate the state to the DF. It sent the route type 7 to the DF. Now the receiver decides to leave this group. And it decides that I'm going to send the leave to PE4. No problem. PE4 is going to advertise the IGMP leave sync route, or the new route type 8, and send it to the DF. So now the DF, again, has all the state about the join, about the leave, and then it can decide to generate the SMET route towards the core or not to pull down the traffic, right? So again, to summarize, we have 2 new route types which map to IGMP join and IGMP leaves. The mechanism is similar to what we have in MVPN. We convert them to BGP updates. And because they are converted to BGP updates, now you are not sending your IGMP join and leave traffic over the core, right? Every 30 seconds you have something coming in. That's not going to the core anymore because it's all collated at the DF. If the DF has sent the join once towards the core, it doesn't need to do it again if more receivers join. So you're reducing the amount of bump traffic in your multi-access segment and also impacting the core. So that's the use of 7 and 8. Now we build on top of 7 and 8, and we start to utilize route type 6. The DF is the only guy that sends out route type 6. When it decides that it has receivers that it needs to pull data from the core, it's going to generate the route type 6. The whole point of this route is that if I'm a PE and I don't have any receivers for a particular group, I don't want the traffic for that group. If I send the SMAT route, I see traffic for that group. If I withdraw the SMAT route, I stop seeing traffic for that group. So I think the only thing that I want to point out over here is that you will notice the packet format is very similar to the route type 7 and 8. But again, if you focus on the top 2 rows of the fields, you'll see that the ESI field is missing. In the previous 2 packets, we had the Ethernet segment identifier as part of the packet. But we don't over here because we don't need it, because now we're dealing with the core. I just need to know that I have a receiver. I don't care which ESI segment it belongs to. As long as I have a receiver, I'm going to need the traffic for it. So this route doesn't need the ESI field to be part of the packet. So we'll go over just a couple of scenarios. So for example, now I have the red and the green group. PE2 and PE3 are part of the green group. PE3 and PE4 are part of the red group. So PE3 will send out SMET routes to everybody else inside the L2 domain. For the red group, the same thing will happen, but in this case, because the red group, the receivers are only present on PE3 and PE4, it's just PE3 and PE4 that are going to send out the SMAT route, but they're going to send it to everybody. Now, PE1, which finally is the one that is responsible for sending the traffic out, for sending the data out, it's sending the red data to only those PEs that have red receivers. So if you focus on the red lines, PE1 is not sending the red data to PE2 because it did not receive an SMAT route from PE2. So the base method of replication, ingress replication, you want to optimize further on that. You can start using P2MP tunnels. You can further optimize on P2MP tunnels using the SMAT route. And now, I'm not going into the complications of bridge domain, how many trees, how many tunnels, a tunnel per BD, a tunnel per EVI, shared tunnels, that kind of things. These are all, topics that will need more than 20 minutes. So, but essentially the SMAT route is your friend. It's going to help you optimize traffic inside the core. I want to close with one slide. Essentially, this is food for thought when you go back and try to think about how this is actually going to be useful to you. So I'm picking a very simple example over here. We have a data center that is a EVPN fabric that is running all these multicast optimizations that we spoke about. Now, this data center needs to talk to an external network, and we need to be able to connect sources and receivers that are part of the EVPN network to sources and receivers that are not part of the EVPN network, which are just part of, say, a PIM or an MVPN domain. In that case, the gateway, which is sitting at the edge of your data center, obviously it's able to talk EVPN and also PIM or MVPN. So your SMAT route in this case, let's say I have a receiver, the blue receiver, sitting inside the data center, but the source is external. It's not part of the EVPN fabric. So what does the gateway do? The gateway converts the SMAT route into a regular PIM join and sends it to that external M router sitting up in the cloud. And at that point, to that external M router, the whole EVPN fabric just looks like a CE. We have a similar use case for the reverse traffic flow in the reverse direction. I have seen use cases where folks wanted to employ a gateway for inter-subnet routing. We haven't even touched inter-subnet routing at all. That's when your receiver is, say, in the red domain and your source is in the green domain, and you want them to be able to talk to each other, right? They are in separate bridge domains. In that case, you could employ a gateway, again, use the SMAT route to be able to do that inter-subnet optimized multicast routing. These are just some of the use cases. We'll close with some of the reference material that was used. So the first URL up here is essentially what describes these optimizations, your route type 6, 7, and 8. The SMET route, which is used for optimizations in the core, and then route type 7 and 8, which are a reflection of the IGMP join and the IGMP leave, and they help optimize the multi-access segment. For further reading, optimized inter-subnet multicast routing, that's draft LIN, that's the last URL. This is all I had today. Thank you for joining, and we'll open it up for questions. Hi.
Hi. Thanks for a great presentation. So the question is on Jeff Tensura NOASH networks. Type 6 origination. So in EVPN, we would have data-driven switch to data MDT. Here, is it bound to DF election? After DF election is done, would you start advertising? What happens on re-election?
So I'm not familiar with the nitty-gritties of how it integrates with the DF election, but yes, like I said before, it has to be just the DF that is going to advertise the SMET route.
So when re-election happens, election is a dynamic process, would you withdraw SMET route and re-originate it?
Yes, I would imagine, because it's only going to be the DF that's supposed to do it, so you can't have multiple guys sending it out.
Okay, thanks.
David Farmer, University of Minnesota. We're in the middle of all of this and in the deployment of this EVPN technologies for campus. And we've run into the multicast questions, particularly when you're combining multicast with Anycast gateway and then your multi-access, and it gets rather complicated. I didn't see any mention of the Anycast gateway kind of issues in this. Is that sort of in the drafts as well? Or?
No, it's not in the drafts as well.
Okay.
That's not, so I think we are working on putting it in the draft LIN, the second draft, so that's
Okay.
something that's still being worked on.
Okay.
But essentially, I guess your question is how traffic is load balanced across those gateways? Is that the?
We're not doing it for load balancing, we're doing it for resiliency. So
Okay.
we want Anycast gateway for resiliency.
Okay, so then in this case, you would have Anycast DFs, or you would have?
Well, yeah, do you do DFs, Anycast
Anycast,
DFs,
okay, the
or
standard
how
question.
do you want to do that? Yeah.
Right, okay, yes, I think that's something, obviously will depend on the architecture. It's a very valid question. Like I said, EVPN and multicast in itself, they're complicated to begin with without combining them. So yeah, we're working on it.
Any further questions? All right, let's go ahead and thank Disha for her presentation.